Okay. On Monday, we introduced the instantaneous power for this very simple AC circuit. Instantaneous power is basically just defined as just the product of the instantaneous voltage and current. You just multiply their values at time point by time point until we get this expression. So for this expression, we want to use the RMS value, the root mean square value for voltage and current, because they are more meaningful values related to power. So this complex expression also involves the angular frequency of this AC circuit and also the voltage angle. This is the voltage angle relative revolving reference. Another angle theta is the angle by which the voltage is leading the current. So which is the angle difference between the voltage and current phasor. So if we know this expression, we can know exactly what this instantaneous power can change in the time frame. But that's very complex. So at the end of Monday's lecture, we also introduce some concept about like powers, the complex power, real power, reactive power, which just very useful ideas to simplify this instantaneous power without loss of any information. So we talk about this example. We just gave it some value, such as you can have the instantaneous power expressions for this specific system. So you see that formula is largely simplified because we have changed all. We have plugged in the values such as the RMS value of voltage, current, such as we can largely simplify the amplitude of the two items, and so which will become just the two numbers. So here there's a 2000, which is the tell about the variation of the first item, and 3464 is the variation of the second item. And we call the first one is the PR, second one as the PX. So there's some reason because R and X indicate the resistance and the reactance of the circuit for the load. So if the reactance is 0, so actually you can prove the second item will be 0. The first item is this if there's a resistance. If it's purely resistive load, the impedance is just resistor. So this is a load consumed by the resistor. But if they also have some inductance or capacitance, the second item will be non-zero. We show those waveforms. The first one just compare the waveform of the V and I. So here we assume I is lagging the V by 60 degrees. So that can be told from the angle of the impedance. So that 60 degrees is actually the theta by which the voltage is leading the current. Then next, you just multiply those two waveforms point by point, you get a second waveform. And here is 0. And this waveform is also sinusoidal waveform, but it's finish 2 cycles in one period of original voltage and current. So which means this is faster, twice as faster as the voltage and current. And those two actually the first item and second item. As I said, the first item exists if the load has resistance, and the second item if it has reactance. So for the first item, if you calculate the average will be 2000, which is exactly the value at the beginning of the first item. The second item will have amplitude. If you measure the amplitude, here is a 3464. That's the number at the beginning of the second item. Okay, so we know. So the first item, if you integrate the area under the green curve, that will give you this rectangular area. That tells the energy consumed by the load for one cycle. But if you integrate the blue curve and under the blue curve and also zero, you get nothing. You get zero because this area equals that area. So they will cancel out. Okay, so only the first item indicates some real energy consumed by the load. The second item doesn't cause any energy consumption, but it tells a certain pattern for the load to exchange energy with the source. So for example, if this area is positive, which means for this 90 degree, okay, so 90 degrees is a quarter of the full period of the voltage current. For this 90 degree, the energy consumption by the load is positive. But in the next following 90 degree, that consumption becomes negative. So basically this device consume this energy and give it back to the source, then consume energy, give it back. So this 3464 only indicate a pattern on how the load is exchanged with source for the energy. Okay, so think about it, if you make this angle be negative. So here, this 60 degree is actually the theta. If you make theta be negative, so in this formula, okay, this formula doesn't change, right? So that's the magnitude of the voltage and current. They will be same. Cosine theta, if theta become negative 60 degree, cosine theta will be same. Okay, so it's equal to half. But sine theta will become negative. So this here, this one will become sine negative 60 degree. So which means this blue waveform will change to the opposite. So this part will become negative and this part will become positive. So the load will first generate some energy, give it to the source, then get the same amount of energy back in the next 90 degree. But the load is exactly the same. The first item doesn't change. Okay, so let's summarize our observations. So instantaneous power have two items. So they both vary twice as often as voltage current. The first item is the first item will never be negative. It will be either zero or positive, but most of the time it will be positive. So if you integrate the area for the first item between the first item and the zero, it will give you the value 2000, which is exactly the number in front of the first item. And second item is another sinusoidal waveform. The integration will be zero, but they tell how the load is changing energy with the source. So those are our observations. So at the end of the Monday lecture, we also gave those basic idea about different definition of power, all based on this instantaneous power expression. First, we introduced apparent power. Apparent power basically just the product of the magnitudes for voltage and current. So we call it apparent power. Because we know theta can change. Because in the system, if the voltage can vary the angle in dynamics, but if we can maintain the voltage, current, magnitude be the same, apparent power will be same. So apparent power really indicate the loading level of the system. Okay, which means when the theta becomes zero, so the first item will completely become apparent power. So that could be the maximum power your load can consume from the source. So when the theta becomes zero, so we call it apparent power. It's apparent power. It's not really a real power. So we are a little bit hesitate to use the watt, the conventional unit for power. We just call the unit as volt ampere or VA or kVA or MVA. Could just indicate that's different from actual power, or maybe just call it VA until we know it is really the real power, not real power. Then this item is really the real power because that indicates the power of the load, okay, of the resistive part. It is just, so this is the equal to the number 2000 in that example. And this one is really real power or active power. You can call it either way, or just it's actually the average power. So we can use the unit W. Then this factor actually indicate the ratio of the real power to the parent power. Okay, so if the theta is changing, we know with the same parent power, the real power will change with theta as cosine function. So we call that cosine theta as a factor. We call it a power factor. The power factor will vary from 0 to 1. Okay, when the theta is equal to 0, power factor is 1. When the theta is non-zero, it will be less than 1. But cosine theta doesn't tell the sign of the theta. So we still need to give another piece of information to indicate the sign of angle. Because if theta is positive, we just call it a lagging power factor. That means the voltage angle is bigger than current angle. So lagging means the subject is actually current. Lagging power factor means current is lagging voltage. Because usually voltage will be controlled in the system. So usually the engineer will select some voltage as a reference. So lagging power factor means the current is lagging voltage. And if a current is leading voltage, which means this angle becomes negative. So theta I will be bigger than theta V. So we call it the leading power factor. So subject is a current. So for this case, it's lagging, right? This case, that's lagging. So leading will be something like this one. Okay, for the number at the beginning of the second item, we call it Q. That's a parent power multiplied by sine theta. So this one is called the reactive power. This is the number of 3,464. That indicates how much the load can change energy with the source. But that doesn't cause any actual energy loss or consumption. So we cannot use volt. We cannot use W. We call it V ampere reactive. So for short, it will be VAR, either all capital or the last one lowercase, or the only first one capitalized. So usually if you don't know which one is better, I recommend you just keep this one so that there's no confusion in any literature. So because theta, when theta has positive negative sign, that will be reflected to the sine theta. So the Q can be positive and negative. So positive Q means the theta is positive, which means voltage leading current. So that is the inductive load. Okay, because only for the inductive circuit, inductive branch, the current will be lagging the voltage. If theta is negative, that's a capacitive branch, capacitive load. So Q will be negative. So negative Q means usually means a reactive source. Positive Q means reactive load. Okay, I use this figure to give you an idea on what is Q, what is P. So this cup is actually the capacity of your transmission line or device. How much beer you can carry, right? This is H. And when you put the beer into the cup, depending on how you do it, so you will always have some beer head, okay? So if you're very skillful, you may be able to minimize the Q. So you can fully utilize the entire capacity at the beer or soda. But if you don't do it correctly, so you maybe have the full cup of a Q. That's possible. Okay. Yeah, this just gave you an idea. So okay, there's a fundamental question you can ask anybody. If anybody claim they're working in the power industry, they're a power engineer, or they're serving power engineer, you just ask the question, can you explain to me what is Q? What is reactive power? Because there are many researchers or many people working in the power industry, they don't directly deal with Q. They may focus only on P. They don't have to explain the meaning of Q accurately. So let me give you more mathematical insight of what is P, what is Q. So, okay, so we know because we call the voltage as phasor or vector, we can use the real part an imaginary part to indicate P, right? VR will be because P, the voltage is complex number. So you'll have a real part and imaginary part. And current also has real part and imaginary part. So P is actually just I dot V, which is the inner product of a current and voltage vector. So you know when you have two vectors, you calculate the inner product, that actually only care about the angle, right? If the angle is 0 in parallel, that's a maximal inner product. Or in other words, if you have a current voltage each as vectors, so you can, that's the inner product. So active power is really the inner product between the voltage and current vector. Then what is Q? So in the vector algebra, so you can easily prove Q will be equal to this one. If you're familiar with this expression, that's cross product. Okay, so cross product, when they have orthogonal to each other, they will reach the maximum value. Okay, any question? Does it make sense? Okay. Okay, then next one. So when you read some power system report, they always, some engineer will say, okay, well, our system is in the lack of a reactive source. We need to maybe deploy more reactive source. So what does reactive source really mean? It doesn't mean battery. It doesn't mean generator, right? That does not necessarily mean a generator, but it means a source of reactive power. Okay, just use this one as an example. So we have current lagging voltage by 60 degrees, and this is the reactive power. This is the part of instantaneous power that causes reactive power. So reactive power really means this magnitude. And for that example, we know for this case, the Q is positive because we treat the load as load, and this Q also as load. So we call this pattern of Q or instantaneous power as reactive load. So reactive power of a circuit element results in no real energy consumption. So if you have a device, for the first item, the PR is 0. It's exactly 0, but it only have something like PS. So which means this device doesn't cause any real energy consumption or contribution. But the Q can be either positive or negative, depending on the pattern of this waveform. So as I said, for this specific waveform, that is a positive Q. That's a reactive load. Okay, so let's see, we start from the moment of when voltage reach its maximum, which is time 0. Okay, and for an inductive element means the lagging power factor. So we'll first consume some energy, right? And then we'll give the same energy back to the source, to the system. So we call this specific pattern as reactive load, which means it's absorbing reactive power. So if any device behave in such way, using the reference of voltage at the peak value, so this is called reactive power load or absorbing reactive power. So if your system has such device, it will help reduce power swing. So later in the line modeling session, we'll talk about why such devices are able to limit the power swing. So compared to this pattern, there will be another pattern. So you'll have going to the opposite. So you this part will first become negative, then positive. So negative means it is not a positive load; it's a negative load. Negative load means a source. So it will generate some energy and give it to the source, and then retain the same energy back. Then consume the same amount of energy. So this is a leading power factor. So compare lagging power factor for the first case. So we call the second pattern as generating reactive power or reactive source. Okay, so just to make it simple, reactive source just means any branch or any equipment behave like a capacitive load. It's capacitive, it will be a reactive source. Otherwise, it will be a reactive load. So in long transmission lines, the low voltage usually will happen at the receiving end. We'll prove this statement, but right now just keep in mind this statement. So for long transmission, power transmission, usually the low voltage will at the receiving end. So usually that can be a reliability concern because we don't want the voltage to drop too much over the distance. So if you want to make the voltage higher, usually they will purchase the shunt or series capacitor depending on how it's connected to the line. It can be connected as a parallel branch to the load or in series with the transmission line. So usually such capacitors are called wire sources, or any other device which can behave like capacitor. It may not be real capacitor, but it will behave like capacitor to make a current leading voltage. So such devices will be considered wire sources. Wire sources means reactive power sources. Any question? Okay. All right. So we already defined P and Q separately. P will be the average power, right? Q will be how the load and source exchange energy. And we also define S as absolute value, which is apparent power. So it's very natural we just define a complex power. Because from here, this is P, this is Q, and this is S, absolute S. So if you look at those three items, you can easily think of, okay, probably S itself is meaningful. It can be a complex number, has real part as P and imaginary part as Q. So to calculate the real part, it will be a absolute value multiplied by cosine theta. Theta will be the angle of the complex number. So we can naturally define complex power. So this is definition. So complex power is not like a real physical thing. It's just engineering definition, just for convenience of a calculation. Because we already make a voltage current be complex numbers by introducing the concept of phasor. And we also define the voltage divided by current as impedance. Impedance is also another complex number, right? Real part is resistance, relative part, imaginary part will be reactance. And now we also make a power be a complex number. We call it complex power. Okay, so we know the magnitude will be apparent power, and theta here is the same theta between voltage and the current. So if you know P and Q, you can calculate the apparent power using this Pythagorean theorem. And for complex number, we can, if we draw the complex number in the complex plane about the real axis and imaginary axis. So P will be like in the real axis direction, and Q will be parallel with the imaginary axis direction. So as this head will be a complex number. So that complex number will be the whatever you calculated for S. So the angle here is the same as the angle between voltage and current. So we call this triangle as power triangle. Next, we know this is apparent power, this is theta. And we want to find an easier way. We don't want to use this formula all the time to calculate complex power. We want to figure out how to calculate complex power directly from voltage and current phasors. So first, we make a theta be just a theta v minus theta I, and we give us theta v back to voltage and theta I back to current. But because here we have negative sign, so we have negative sign, negative theta I with current. So the first item is actually the voltage phasor, but second item is not voltage phasor because we have changed the angle. That is actually the conjugated value of current phasor. So this is the first very important formula for the entire course. If you forget this formula, you don't know do anything else. Okay, you will be stuck at every single problem in homework and test. Okay. Remember this formula. Okay. So compressed power is equal to the voltage multiplied by conjugated current. And this is very convenient to calculate power. All right, next. We know the power factor is defined as cosine theta. The sign of a Q will tell the lagging or leading power factor, right? And for when we see something is active load, which means the P has to be positive. Otherwise, it's not active load. Active means it will have some real energy consumption. But when P is positive, only need to make the theta be in the first quadrant or fourth quadrant, right? So the P will be pointing to the right-hand side, not the left-hand side. If P is to the left, that will be negative P. So for this case, that will be active power. But the theta can be either positive or negative. So that can be taught by calculating this one, this Q divided by P. That will tell you tangent theta. So if a tangent theta positive, which means S is in the first quadrant. If it's negative, it will be in the fourth quadrant. Positive theta means lagging power factor. Negative theta, lagging power factor, and the Q will be positive. Otherwise, it will be Q will be negative, which is reactive source as we define. The next, we can take a look at the impedance. Because impedance defined as the voltage phasor divided by current phasor. So it has real part and imaginary part, and also this absolute impedance, and also the theta. So if you compare this one with this one, okay. So which means the P is similar to R and Q is similar to X. So we can draw another triangle also about this theta. So those two triangles are similar to each other. So this directly tell R will be the reason causing P, and S will be something causing Q, and they have exactly the same angle. So we can summarize the formulas we have. So we start from the definition of compressed power. So if we replace the voltage by the product of impedance and current, we'll have this one. And I is complex number multiplied by its conjugate, it will be absolute value squared. Okay, the Z will have real part and imaginary part. They will have two items. The first item will be P, the second item will be Q. So if you know the current, squared multiplied by R or X will give you P and Q. So those are the formula you can utilize. So we know the P will be this one and the Q will be that one. Okay. So those formulas could be useful in your homework. Next one, we know apparent power is proportional to the current, the RMS value of current squared. Usually we'll use either S or the current square as the rating of the power equipment. So usually when you see the rating on the plate of some device, usually that means apparent power, because power factor can change in the system. But as here, apparent power really indicate the capacity of the device. So next, let's take a look at. Let's go back to this simple circuit. So now we have get rid of all the sinusoidal waveform. We just use all phasors, all complex number to model the circuit. So we have current phasor, voltage phasor, and we also have the load impedance. And we define polarity like this one. We draw this equipment as circle. We just assume this is source, but you actually can define anything to be source, because in AC circuit, temporarily any branch of the circuit can consume energy or can generate energy. So we don't worry about their actual role. We just define the first item will have this terminal as a positive terminal, and the current is leaving from positive terminal. So if you have any device, okay, connected to the circuit, if you default, let's call this one to be positive, and the current is leaving from positive, you just assume this device behave as source in your calculation. But whether it's really a source or load, it doesn't matter. You just do the calculation. You finally number that tell you is positive number, it just indicate that for that moment they behave like source. But in some other condition, it can be negative. It will become a load. Okay, so in AC circuit, we don't really worry about their actual behavior, but you have to assume the role for each device. So now we just assume the left equipment is source, the right equipment is as load. Okay, but there will be some possibilities. Okay, so if we use current as the reference to draw the phasor diagram about voltage and current. So we assume the current will have angle 0. So for this case, we assume theta I is always 0. So let's just assume theta I is always 0. Okay. Then this angle will between the voltage current will be theta V. So I draw the four possibilities. Okay. So voltage can be in the first quadrant, second quadrant, third quadrant, or fourth quadrant. So if it's second quadrant, which means this is theta 2, right? There's a, and this is theta 3. Oh, sorry. And theta 4 will be all the way here. So theta can change from 0 to 360 degrees. Then for those 4 cases, how do we know the real role of this load? So we have to calculate the complex power. Then using the complex power, we know P and Q. Based on the sign of the P and the sign of Q, we know their actual behavior, okay, in that condition. So we just put this table. So let's guess for the first case, if we only put like positive and negative here, so for the first case, so is this positive, right? Because that's related to cosine theta. Theta is between 0 and 90 degrees, so this one has to be positive. This is also positive for the V1 for the first case. And the second case, in the second quadrant, so cosine theta will be negative and sine theta will be positive. And the third one here, both will be negative. And last one, P will be positive and Q will be negative. So they are all 4 possibilities. So if you visualize the calculated complex power, so in all the 4 quadrants. So based on sign, you will know it's a load or source in terms of active or reactive power. Because impedance triangle is similar to complex power triangle, so we know also that Z1, Z2, Z3 also in that direction. So it's up to you when you have such a problem to figure out the real role of some device. You either calculate the complex power, then you put the complex power in the 4 quadrant to see which quadrant it really fall into. Okay, if it fall into the 4th quadrant, it will have negative P and a negative Q. You can also decide to calculate the impedance. And because impedance will be parallel with the complex power on the complex plane. So either one, whichever is convenient to you. Then based on this figure, you will know it's really the active load or reactive load or active source, reactive source. Okay, so let's summarize. The first case, both P and Q are positive. So this device is load in both active power and reactive power. It consumes energy, real energy, and also consumes some reactive power. And second will be a active source, but the reactive load. Third will be active source and reactive source. So for the third condition, if voltage fall into the third quadrant, this is actually the source for both P and Q in the circuit. Even we assume this one to be source, it really behave as load in both P and Q. The last one is actually the positive load and active load, but a negative reactive source. So the first one corresponds to inductive load. It's like a resistor connected with the reactor. And this one is like a generator, but which can absorb some reactive power. And this is a generator supplying some reactive power. So we'll explain why the generator can switch between those two different operations. The last one will be a capacitive load, which is like resistor connected with a capacitor. Any question? Okay, so here's a summary of some useful formula you can use for homework and test. So if you use this form, you can easily prove everyone. If you know the voltage and impedance, including the resistance and reactance, if you want to calculate P, you may easily just think of this formula from a DC circuit, but you have to be very careful. If you use this formula, that only happens if X is 0. Okay, if X is not 0, this formula is wrong. So my suggestion is the easiest way is just, if you know the voltage and impedance, always use this one. Okay. And then you take a real part to be the P, imaginary part to be Q. Yeah, so those similarly, this one only happen if the resistance, only the resistance is 0. So those two formulas can be used, but you have to be very careful. But if you know the voltage and impedance, it's better to start with this formula to calculate P and Q. So let's talk about one important and very useful principle in power system, which is complex power balance. So let's assume we have a more complex circuit with a single source supporting 3 branches connected in parallel. And you know the first branches only have a resistance. The second branch also has resistance and inductance, and the third one resistance and capacitance. So they will have very different load impedances. If we calculate the total complex power from the source, you can definitely use the voltage and current both at the source side. So you just directly calculate the product of voltage and the conjugated current. That will be the complex power. Or you can calculate the complex power at each individual branch. So then the total will also give you the complex power. And you can tell, actually those two formulas is actually connected by this part. This part in the parentheses that indicated total current. So that is actually the conclusion of Kirchhoff current law. So if you apply to this point, all the current in will be equal to the sum of the current out. Okay, so that can be proved by Kirchhoff current law. So directly we can prove for this circuit, the complex power from the source is the sum of the complex powers from all the branches, all the other branches. And such balance can be maintained in both active power and reactive power. So if you only calculate for the active power, that balance is same. For the reactive power, also have the balance. Then we can give such a principle for the complex power balance. So for networks supplied by independent sources, all at the same frequency. So this is very important. This assumption, all at the exactly same frequency. So that will be necessarily true for steady state analysis because we focus on steady state. Steady state, we have everything like a frequency, including frequency, voltage, magnitude, current magnitude be constant, right? So in steady state analysis, this assumption is true. So if this is true, and all currents and voltage assumed to be sinusoid of the same frequency, and the complex powers supplied by all independent sources together will be always equal to the total complex power consumed by other branches. So which means if you for such circuit or any circuit more complex than this one, if you know exactly, okay, this guy is a source, those will be not source. So you calculate the complex power for all sources like this one. That the total will be equal to the all complex power consumed by the others. So that will give you this equation. So left-hand side, you just submit complex power of all actual sources or anything you believe they are sources. And on the right-hand side, you just calculate the complex power of those branches. So when you calculate complex power, you have to define the polarity, which means for the source, you assume when you calculate complex power, you use the voltage and the current leaving the positive terminal. When you do the calculation for the others, you use the current go into the positive terminal. Okay. So that is consistent with our assumption about how we define source or load in the AC circuit. So then this equation will hold. Okay. But you may wonder, but what if I don't know which device is source or load? How do I know this one is source? Oh, definitely here I put like a positive and negative sign there. It looks like source, but in real power system model circuit, it can be very complex. So this one may indicate a solar farm connected with batteries and also maybe diesel generator. It's just like a microgrid. When I do such calculation at certain condition, how do I know this system really behave like source? So the balance of a complex power law or principle tells it doesn't really matter. Okay, you can just feel free to assume this one to be source or load. If you don't want to differentiate maybe some branches as source, some branches as load, make it simple. Just treat everyone to be source, everyone to be source, or everyone to be load. That's the same. So if you treat everyone to be a source, which means you move everything on the right-hand side equation to the left. But be careful when you move any item from right to the left, you have to treat that branch as source, which means you use voltage at the positive terminal and also current leaving the positive terminal, which will be this formula. You just treat everyone to be a source. Okay, you calculate as a source. Then right will be 0, which is just like the entire system has to be balanced for the energy. If someone generating, someone is consuming, and if you treat the generating as positive, consuming as negative, you put them all to the left-hand side, they will make up, finally will compensate each other. So right-hand side, you get 0. Or you treat everything to be low, that's fine. The left-hand side will be 0. So either way is good. Okay, how do we apply this rule? So any portion of a power network may be replaced by equivalent independent source or load as long as the power balance is maintained. Okay, so for this system, I can easily just replace the 3 branches together by a single element as long as that single element is consuming exactly same complex power. So later we'll show how we apply this principle in some real examples. Before I move forward, I have to clarify. So we call it the principle of complex power balance. It is different from conservation of energy law. It's not a conclusion from conservation energy law. And this is the engineering principle, not the physics principle. Okay, because conservation energy law has to be true. Or in other words, for this case, we have 2 conclusions. We have a balance of active power and balance of reactive power. I have to say, if I keep only one to be accurate, this one is somehow more accurate. This one maybe not. But that is good only when you have under the steady state condition, or at least the voltage current all at the exactly same frequency. Because later, when you get a chance to study the real system uses, there are a lot of harmonics. So here we have ignore all the harmonics, right? When we introduce the simple circuit, we assume voltage current is operated at just single frequency, very smooth sinusoidal waveform. But in reality, if you measure the voltage current, sometime will become rectangular or triangular. So which means the current is not just single atom. There will be maybe some other atom, which is like third harmonic. There's 3 times omega plus some angle, right? There will be fifth harmonic, seventh harmonic, or maybe those odd number or even number. There are many such items. So when you average the power, okay, that average power or active power can be balanced. But the reactive power, remember how we define reactive power. We define how the load and source they change energy with each other in certain pattern. So we use the 1 period for the omega, for the fundamental frequency as period to discuss the pattern. But if you have more harmonic, for each harmonic you need to define reactive power. So you may have many different components of reactive power. So when you maintain the balance of compressed power, you need to cover not just the fundamental frequency, you need to cover all the frequency component. Okay, so yeah, next one is just very simple example. It doesn't take much time. So if I give you a number, you can calculate the compressed power for each branch using this formula. So if you know voltage and also impedance, you can calculate the compressed power. And you calculate the total, that will give you the total compressed power. Or you want to make it simple, you just define everything on the left-hand side as a single device. That will be the total admittance, which is the reciprocal of impedance. And you can get the same answer by one calculation. So I pause here. We'll continue on Friday.